Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we are continuing with the third part in our series on stereochemistry. In this lecture, we'll be looking at the shapes of cyclic molecules and the actual three-dimensional structures they adopt. The simplest ring structure, or cyclic molecule, is the molecule cyclopropane. Now, cyclopropane possesses carbons that have two carbons bound to them and two hydrogens. So each carbon atom has two bonds to carbon and two bonds to hydrogen. Or it has a hybrid orbital number of 4. HON is 4. There are no lone pairs. Because of this, each carbon is sp cubed hybridized, tetrahedral in shape, and the bond angle is equal to 109.5 degrees in sp cubed hybridized systems. However, cyclopropane is an equilateral triangle. In shape. And the angles in an equilateral triangle must add up to 180 degrees. Since this is 3 angles, if we divide 180 by 3, the actual bond angle gives us a bond angle of 60 degrees. Okay. Clearly, there is a deviation between the expected bond angle of 109.5 degrees and the observed bond angle of 60 degrees in an equilateral triangle. This deviation between the two angles equals 49.5 degrees. The larger the deviation, the greater the strain will be in the ring structure. And the strain, when it comes to angles and deviation in angles, is referred to as angle strain. Now, angle strain simply can be defined as a strain in a molecule caused by some factor that makes the bond angles deviate from normal. So any factor that causes this type of deviation is angle strain. Okay? It's a strain in a molecule caused by the deviation in the angle. The angle wants to be 109.5, and it can't be. Why is that? Well, suppose we look at 2 of the carbons in the ring. So we're going to look here. We've got another one over here. Here's our cyclopropane. The orbitals actually do point, the sp cubed orbitals actually do point to angles 1.95. But the bond that we draw is along the dashed line. That is, the orbital overlap is not occurring at the closest straight line distance that we see between the two atoms. So the apparent angle of 60 degrees is actually not the angle the orbitals adopt. Now, but because the orbitals are not directed at each other, there is less orbital overlap. And because of the angle strain, the bonds are weakened. We attribute this angle, this bond angle, or angle strain, as causing the weakening of the carbon-carbon bond. But in actual fact, it is the poor orbital overlap that results from the orbitals not being directed to each other along the closest straight line distance. Well, you may ask the question, shouldn't we symbolize then the bond by, let's use red here, this line? Shouldn't the bond be where the orbitals go? Shouldn't we be drawing bonds like that? You must remember our definition of bond. Bond is the closest joining, closest distance, straight line distance between two atoms in valence bond theory. And so drawing a curved bond showing where the orbitals are actually overlapping, well, just isn't appropriate. Now, you should note also that I am exaggerating the amount that these orbitals actually deviate from this, just to make my point. But the deviation of 49.5 degrees is in fact an artifact of taking this closest distance, taking this as my bond angle, taking these as my bonds. Okay? So you get the idea. Now, it turns out if I take a look at this molecule edge on, I'll notice something else, especially if I look down one bond. It turns out that the hydrogens are eclipsed. Okay? The hydrogens are eclipsed. Now, as we've discussed in our previous lecture about conformational analysis, eclipsed groups are in a higher energy state. The atom would like to, because of the repulsion in the electron clouds, get these hydrogens further apart by staggering them. To stagger them, there must be some rotation. Okay, some rotation about this carbon-carbon single bond. Now, that is a twisting motion in the ring, and twisting is referred to as torque. And so the strain caused by eclipsed hydrogens is referred to as torsional strain. So not only do we have angle strain caused by this deviation, this 49.5 degree deviation, we have torsional strain. Torsional strain, which is trying to twist the carbon-carbon bond to stagger the hydrogens. Now, because it's a three-membered ring, this cannot be done. So the torsional strain is really the strain resulting from the repulsive forces between the eclipsed hydrogens. Okay. If we take the angle strain, and we add with it the torsional strain, we get the total ring strain of the system. So ring strain is the sum, if you like, of angle strain and torsional strain. Now, because of the eclipsed hydrogens, the torsional strain, because of the heavy amount of angle strain, Cyclopropane is one of the most strained cyclic rings one can generate. By the time we get out to cyclobutane, we have significantly reduced our angle strain. So here's cyclobutane with a few of its hydrogens showing. Now, if that's an edge-on view. If you look straight down on it, it would look like a cube. If cyclobutane were a flat square, the bond angle would be 90 degrees. Again, carbon has 4 bonds to it, a hybrid orbital number of 4, it's sp cubed. We want a bond angle of 109.5. Okay, so we want a bond angle of 109.5 degrees. Perfect square gives us a bond angle of 90 degrees, a deviation of 19.5 degrees. The angle strain is significantly reduced in having a square rather than an equilateral triangle when we compare to cyclopropane. The interesting thing is that if we actually do the crystal structure, cyclobutane is not flat. It is actually a puckered structure. And because it puckers, the angle is further strained. The puckering produces an angle somewhere around 88 degrees. Now why would a ring increase angle strain? If it's 88, we add 2, we're now at 21.5 degrees deviation from the 109.5, and that's an increase of angle strain. Well, clearly, if the molecule is increasing its angle strain, it must be getting some payback in energy. In other words, if angle strain is going up, something else is going down, so the ring strain can be in total reduced. Now remember, ring strain is the sum of angle strain and torsional strain. So if we're increasing angle strain, we must be doing something to the torsional strain that's beneficial. Now remember, torsional strain is caused by eclipsed hydrogens. And if I look at the hydrogens in the flat cyclobutane that I've drawn edge on up here, yes, the hydrogens are eclipsed. What's interesting is if you look down, the bond when it's puckered and the bond angle's increased to 88 degrees, the hydrogens are now staggered. And the repulsion between hydrogens is reduced. Now, the only reason the bond angle would increase to an angle of 88 degrees is if somehow the torsional, the staggering of the hydrogens, reduced the ring strain more than the angle strain increases it. Overall ring strain, the molecule is going to try to minimize ring strain. And if it can do it by increasing angle strain and getting more back by relieving torsional strain, the molecule will. So you need to be able to explain why cyclobutane adopts a bond angle of 88 degrees and not 90. Why cyclobutane increases angle strain. And the answer to that is that by increasing angle strain, it can reduce the overall ring strain. Because by puckering and going to a bond angle of 88 degrees, it staggers the hydrogens and reduces the torsional strain so that there is a net gain in stability and reduction of overall ring strain. All right. In spite of this puckering, you should note that in going from cyclopropane to cyclobutane, we're producing a more stable ring structure. Okay? Well, what's the next ring? The next ring is cyclopentane. Now, we're not going to spend a lot of time looking at cyclopentane, except to say that the bond angles, okay, if cyclopentane were planar for a pentagon, would be 108 degrees. Deviating from 109.5 for sp cubed atoms would generate a deviation of only 1.5 degrees. Well, clearly this is a small deviation, and in fact it can be further reduced, okay, by again some puckering. So we can get cyclopentane puckering like this and folding and twisting to stagger the hydrogens as best it can, reducing torsional strain, and try to get the angle as close to 109.5 degrees as possible. Because of this, cyclopentane is slightly bent. This relieves the torsional strain. The puckering is in constant motion. That is, there's rotation about the bonds, and if you like, this puckered section can flip down. Bad drawing. There we go. And so you can get the molecule undergoing conformational change. Flipping is possible. Because of this, it can minimize the deviation. It can also keep the hydrogen somewhat staggered. Minimizing angle strain and torsional strain reduces the overall ring strain. So if we look at cyclopentane, we would say it's a pretty much ideal ring system with very little deviation. What about if we take a look at cyclohexane? Well, if I draw a flat hexagon, the bond angles are now, in a flat hexagon, 120 degrees. With expected bond angles of 109.5 degrees, we have a deviation of 11.5, or 10.5, sorry, 10.5 degrees. That's significantly more deviation than we expected for cyclopentane. So does that make cyclopentane the most stable and predominant ring structure in naturally occurring organic compounds? In actual fact, it is the cyclohexane. And the cyclohexane can totally minimize, totally get around this deviation of angle strain. And also, don't forget, with deviation comes torsional strain. So if we drew an edge-on view, and we drew our H's, the H's would be eclipsed if we drew it flat with extensive torsional strain. So you'd have significant angle strain if it was flat, significant torsional strain. Why would cyclohexane be the most predominant ring structure for organic compounds? It turns out it can get to a conformation, a shape, that totally reduces and removes the angle strain and totally minimizes the torsional strain. Well, if it's not flat, what does it look like? Well, it looks something like this. Wow. It is bent at both ends. If you like, puckered at both ends. And this puckering totally staggers all of the hydrogens and makes the bond angle at each carbon 109.5 degrees exactly. Now, when I say exactly, please understand there are deviations in bond angles when they are measured with X-ray crystallography, and this is somewhat due to thermal motion, and that can be minimized by cooling the sample. But overall, the ideal 109.5 degree bond angle is achieved. This does not look like a flat hexagon. In fact, if I was to make my character a person, they would look like they were sitting down in a chair. And so it is called a chair conformer. The cyclohexane adopts what is called a chair conformation. Okay, fine. Chair conformation. Now, because of this, we're going to be drawing chair conformers, and in order to do this, you must learn to properly generate a chair. And that can be somewhat tricky. Also, the placement of the hydrogens in a chair conformation can be even more tricky. So we need to give you some rules on how to draw the chair conformer found in the cyclohexane molecule. Okay, so let's do that. The first rule, and I'm going to just read the rules and you can copy them down at your leisure, is to draw two parallel lines that I'm going to label BC and FE. Two parallel lines, so I'm going to draw them at an angle. These are supposed to be parallel. Yeah, try it again. And these two parallel lines, let's label them B, C, F, E. They should start, not only are they parallel, but they should line up. That is, this end, C and E should be lined up, and B and F should be lined up. Okay? Well, that's pretty easy. I can do that. Next, you're going to draw a line AB parallel to DE. So point A is going to attach to B. And it's going to be parallel to DE. Okay. They should be the parallel, same length, and the ends should line up really well. Then you connect C and D and A and F. Now, just so you can see the carbons, because this is a bit smaller display, I'm going to put the points, the dots, on the carbons so you can see where the carbons are in my chair conformer. Now, I am doing this freehand. You can use a ruler, so you can actually make your lines more parallel, a lot neater. And there is a chair conformer. I just want to point out, if you had followed these rules and your initial parallel lines had the opposite tilt, So you're drawing BC this way and FE this way. Then you would have drawn A angled up and D angled down. And when you join them up, you would end up something like that. And so you see what you generate here, depending on your starting angle, is a tilted chair that's tilted the other way. So if you angled them from the upper right down to the left, you get this type of chair. If you B is higher than C, angled the opposite direction, you end up with a chair in that direction. Okay. What do we do next? Well, what you can do on both structures is start putting in the hydrogens. Now, if the vertex, let's pick an atom, B. If the vertex of B, when it's connected at A and C, is pointing up, draw a line straight up. If you pick an atom like C and B and C and D, you know, where C is connected, it's connected to D and B, and you look at the two and C's lower, you put a line down. So going along like this, I'm drawing in some bonds. There's a B. And, okay, so that's down. There's a C. And we just keep going. So we're going to have an E here. There we go. If I do the same thing on the other one, when the vertex points up, when it points down, it's down, up, down. Okay. This is the position of the hydrogen atom, or one of the hydrogen atoms off of each carbon. So you can write in your H, your H, your H, your H, your H, your H, 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 H. Now, because the hydrogens are straight up and down, or these hydrogens, they are referred to as axial hydrogens. That is, the axial hydrogens either point straight up or straight down from the chair. Well, where are the other hydrogens? Well, let's use a different color for them. I'll use red. Now, I'm going to be tracing out some shapes, but I want to show you. Suppose I start at carbon B on the left-hand structure, and I want to put the next hydrogen. It turns out that the hydrogen bond I draw from B, right, points out and away and runs parallel to F. And you notice I sort of generate a Z letter. If you compare the hydrogen to B down and that, you get a sort of little Z. When drawing in these red hydrogens, I'll tell you what they're called in a moment, never draw them in a ring. They always point out and away. You know, some of the blue hydrogens point in the ring, but the red ones never will. So you'll notice you've got line ED. The hydrogen off C is parallel to line ED. Again, it's sort of like a small Z is written there. What about off of D? Well, the red line off of D is parallel, or should be parallel, to BC, this line. So the carbon at E will be parallel to CD. The hydrogen bond off of carbon F will be parallel to AB. And lastly, the hydrogen off carbon A will be parallel to BC again. And this leads to another set of hydrogens that are all pointing out and away around the ring. They're the trickiest to draw, and you should take a close look at them. Notice they never point inside the ring. Secondly, they're all certainly parallel to certain lines that run on the ring, and you have to check which line. If you like, I can write them. This H is parallel to BC, okay? So I'll just put in brackets which one it's parallel to. The H off of carbon B is parallel to AF. The H off of C is parallel to ED. The H off of D is parallel again to BC, and which you could say EF. The H off of E is parallel to CD. The H off of S is parallel to AB. Right? These red H's are referred to as equatorial hydrogens. Now there's something really interesting that goes on here. Think about what would happen, how I could change, okay, and I'm going to just rub off these parallel line designations for a moment. Let's suppose the one that I've drawn the red H's for at this time let's suppose I wanted to change this ring into the ring on the right. How could I do it? Well, if you take a close look, you would see that carbon A could be, if you could grab carbon A and lift it up this way, lift it so that it rotates up and you bend it up so it's above B and F. And then you take D and you bend it down that way. So you drag it down so it appears below E and C. You would get this. Now, you know what's interesting when you do this? Is all of the red hydrogens, all of them, all of the equatorial hydrogens, they become axial. This equatorial one, when you lift this up, it tilts up and becomes straight up and down. So what were equatorial hydrogens become your axial hydrogens. And what were your blue axials? Okay, so I'll put a divider here. Unfortunately, I'm going to not be able to draw it. Well, I guess I probably can. All of the blue axials now become your equatorials. So all of the blue axial hydrogens end up becoming equatorials. And when you do this tilting, lifting of A and pushing down of D, it's called a ring flip. And you're causing what is called a conformational change. Now, it turns out at room temperature, cyclohexane rings are ring flipping like crazy. So if you were to analyze the structure of cyclohexane, you'd only see one type of hydrogen because on average the reds become the blues and the blues become the reds. They're exchanging position, and you don't detect any two different types of hydrogens, one equatorial, one axial. Since they're averaging out and the reds are sometimes equatorial, sometimes axial, you just detect all the hydrogens with an average signal of somewhere between axial and equatorial. You have to actually cool the molecule down quite a bit to freeze out this ring flipping process. Well, I encourage you to take the time to draw this out, this structure out very carefully, so that you can get good at being able to draw cyclohexane rings, because you're going to actually have to draw them and be able to draw the hydrogens properly. Again, notice that whenever you draw equatorial hydrogens, whenever you draw equatorial hydrogens, the equatorial hydrogen never points inside the ring. Axials can point in the ring, and sometimes they do. So the reds became axial. All right. So essentially, structure A can undergo ring flip and become structure B. This is a conformational change. When we lift A and lower D, we're actually rotating about the two bonds. We're actually causing a rotation about those bonds. And therefore, it's a conformational change, just like the rotating about the ethane sigma bond or the butane carbon-carbon sigma bonds. Now, whether it's a conformational change, you can do a conformational analysis. Now, I'll tell you right now, quite frankly, I am not going to ask you to analyze the conformational changes of the cyclohexane molecule. But I do want you to consider some of the things that have to happen before we can ring flip, right? Before we can ring flip from one chair conformer shape into another. Okay, what do I mean? Well, let's just draw a chair, a smaller chair, so we've got some room, and leave out the hydrogens. Okay, I can do that. So we're going to start with a chair, and I'll make it a bit smaller. And I apologize for my poor drawing. And we're going to start with this carbon right here and start moving it upward to begin a change towards the other chair conformer. So at room temperature, we're going from a chair. And the first thing that'll happen is I'll get to a half chair. So if I show dots for my carbons, okay, so this one's untouched. I've raised this carbon. In fact, I'm going to use, I guess, a different color for that carbon. That might be a good idea. So I'm moving this guy. The first thing that happens is I go from a chair conformer. So if this is a chair, I go from a chair conformer to a half chair. Now, once you flatten out the molecule, the bond angle here jumps to 120, so there's a lot of angle strain. Also, the hydrogens coming off the flattened end are eclipsed, so there's a lot of torsional strain. So much so that this half-chair position actually becomes the highest energy state or problem state. Now this is a bit hard to see, but when I raise it up again, there are three conformations that form. So now I have raised the red carbon into its new position. Here it is. And there's actually three conformations in this position. If I was to draw it this way, the three conformations would be where these carbons line up exactly, where they're twisted to different sides, and I'm exaggerating this. Now, these two outer ones are referred to as twist boat conformations. Where the peaks don't line up. They sort of, when it lifts, it goes to one side, it lines up to the other side and twists to the goes to one side, they line up, and then twists to the other side. This is just called the boat conformation. Now the twist boat is higher energy than the chair, but lower energy than the half chair, and much lower energy than the half chair, and lower energy than the boat. The boat is high energy because if you put the hydrogens off the perfect boat form, you get something like this. And these hydrogens off the flagpole positions, if you call them axial, apical, okay, sometimes they're called, these hydrogens right here, they are called axial hydrogens, apical hydrogens, flagpole hydrogens, flagpoles off the bow of a ship, if you like, flagpole. I know flags are not flown usually on the bow, but flagpole, H's. They get in close proximity and there's a lot of repulsion. Now while they're twisted, they're a bit away from each other, but when you get to the full boat, they line up. This raises the energy of the boat, not as high as the half chair, because when it's in the boat, we can get to better angles of 109.5, but there is some torsional strain. And so it's not as high as half chair, but it's certainly higher than a twist boat. So in this drawing, if you like, right here, there are three conformations. There's the one twist boat, swinging to the center where they become boat and line up, and swinging to the other twist boat. Then finally, we can start working on the other carbon and start lowering it. If we do that and start lowering the other carbon, I'm going to erase my boat drawings here. Then what we get I'll draw an equilibrium arrow down, is a new half chair where this guy is up. He's not moving now, so I'm going to make him blue. And the carbon that moved down, I'm going to make red. and we get another half chair. And this is the highest strain position. And then lastly, if I continue lowering it, I get to the new chair. Okay? The new chair looks something like this. There you go. And I'll put dots for the carbons so you can see them. And that is the lowest energy structure. Okay. And so if I was to represent this conformational change with a conformational analysis, leaving out the degrees of rotation, making it a little simpler, so here's E, here's rotation, okay. I would start out at low energy at the chair. I'd jump to a half chair, which is high energy. I'd get to a twist boat, which is low energy, higher energy for a boat, back to twist boat, high energy again for a half chair, and then back down to low chair. I'd end up with something like this. Could look like this. And so if I labeled this A, half chair B, twist boat C, so I'll make C the twist boat, and D the boat. So C and D are represented here. The A is my chair, B is my half chair, C is my twist boat, D is the full boat, C is the twist boat again, B is the half chair, and A is the full chair. Now, as I said, you can do this type of conformational analysis on ring structures. I expect you to be comfortable with drawing ring flip structures. Specifically, you have to be able to take one chair and produce the other chair. I am not going to test you on drawing half chairs. It's nice if you understand the boat and the concept of the boat, but you won't be tested on it. And likewise, I am not going to ask you about this conformational analysis for the cyclohexane ring. But it's useful to see that you can actually do conformational analysis on cyclic compounds. And it's very useful to understand that the ring flip process is not just a simple one chair to another chair change, that you're actually going through a series of structural changes when you ring flip from one chair to the other chair. So if you call this A prime to A double prime. Okay? All right, let's continue with talking about cyclohexane. And let's start putting substituents on the cyclohexane molecule and see if we can answer or ascertain some questions and start drawing some ring flip structures. For example, suppose I drew this molecule, cyclohexane, in a chair conformer. And I'm not going to draw all the hydrogens at this moment, but I'm going to draw in one hydrogen and I'm going to place a substituent. So I'm going to put the hydrogen here, that in the axial position, and I'm going to place the CH3 in the equatorial position. Now I know at room temperature this molecule can ring flip. If I want to draw the ring flip structure, I just tilt the central parallel lines in the opposite direction, and then I draw lines like this, and then it's not perfect, but it works. Now, I'll put dots again to show carbons clearly. You don't have to do that. This is just for the video so you can actually see where the carbon atoms are. All right. What happens to the hydrogen in the methyl when I do a ring flip? Well, remember what I said earlier. Axial positions, when you ring flip, become equatorial. So the H is now equatorial. And equatorial positions become axial. Now you say, well, why didn't I point it up? Remember what I said about vertices. This vertex is higher than the two vertices it's attached to. Because of this, it's pointing up, so I put the H pointing up. Now the vertex is lower than the two vertices it's attached to. Because of that, when it's lower, I put the line down. And so we now have a CH3. Okay, now we can ask some questions about where is it more energetically favorable to place a CH3. Now CH3 is a bit bigger. It has a carbon with 3 hydrogens. If you combine them all, it's much larger than a hydrogen atom. Well, it turns out that having a CH3 group axial is less favorable and higher energy. Why? Well, it turns out these other axial hydrogens, that's going to be hard to see. Okay. These other axial hydrogens here and here actually have repulsive interactions with the CH3. But when it's pointed equatorial, like it is staggered, but all these axial groups, sometimes called flagpole positions, all these flagpole or axial positions lead to stronger repulsions than when the large group is pointed out of the way. Now hydrogen's smaller, so the repulsions reduce when you have hydrogen there. Putting methyl in that position increases the repulsive force, which increases the energy of the structure. That means the equilibrium is shifted to the left. More structures have the methyl group equatorial. How much more? Well, it turns out that approximately 95% of all structures exist with the methyl in the equatorial conformation. They adopt a conformation. At any given time, if you froze the solution out, you would find only 5% putting the methyl axial. So the repulsive energy difference is not great enough to make it exclusively 100%, but the force of interaction is greatly significant. So now, if I said draw, if I gave you a question that stated, draw a methylcyclohexane, I could add the proviso, draw the most stable conformer, or I could say, draw the least stable conformer. In which case, I would draw a structure on scrap paper. And let's say this was what I drew on scrap paper, and it said, draw the least stable. I would know, oh, it's equatorial, it's not the least stable. I could draw the ring flip structure. Or I could draw it the same way, and just put the methyl group axial if I ask for least stable conformer. Now, if I say show all your hydrogens, be sure to put in all your hydrogens, okay? You must draw them properly, and that takes practice. So I encourage you to attempt to draw these things on your own. I will be looking for proper equatorials. They must be drawn properly and parallel to the appropriate lines. If you check this structure, you will find parallel to the appropriate lines. Some of my lines are a bit curved, but I think you can still see what I'm going after here. Okay. Well, now things get a little bit complicated because we have to visit, if we're going to look at disubstituted, and we're going to do that next, disubstituted ring structures, we have to introduce the possibility of geometric isomerism. And if cyclohexane was flat, this would be very easy. You could very easily tell that if I put two methyls on, that this is cis or Z. If I draw 1,2-dimethyl cyclohexane and make it flat, this clearly looks Z. But if it's drawn in a chair conformer, it can be harder to see. So what we want to do is we want to go through and look at all the structures that are possible for disubstituted cyclohexanes and examine, first off, whether the structures are cis or trans, and secondly, is there a more stable conformer and least stable, or if I ring flip, do I generate the same structure? So what we're going to do is we're going to start with a cyclohexane ring, and we're going to put it make it 1, 2. We're just going to draw them anyway and see if we can figure out whether it is cis or trans. So I'm going to, well, before we actually start with 1, 2, let's start with 1, 1 and ask some questions about 1, 1. So let's put 2 chlorines on. Here's 1,1-dichlorocyclohexane. If I ring flip it, I draw the central 2 lines up, draw this down, this one parallel to it if I can. Now I've got it this way. First off, remember when you check for geometric isomerism, if you focus on one of the carbons that bear the 2 groups, and there's 2 identical groups, then there's no geometric isomerism. There is no cis-trans. So in 1,1-dichloro, there's no cis-trans. In the ring flip structure, you see we get 1,1-dichlorocyclohexane, and that is all there is. Now let's try looking at 1, 2. And let's just put the chlorines on in any fashion. Let's add the hydrogens as well. Okay, so let's put the hydrogens. Let's start with the hydrogens axial, just for fun. And I'm going to draw the chlorines in the proper equatorial position. If I drew this chair conformer of 1,2-dichlorocyclohexane, could you tell me very quickly whether it is cis or trans? In actual fact, it's not that hard. You can see that one of the chlorines, if I look at this carbon, it's pointed down slightly. The chlorine's pointed up. And this carbon, which is connected upwards from the carbons it's attached to, its chlorine is pointed down. If you like, in terms of the chair, chlorine pointed down and chlorine pointed up are opposite. And opposite is trans. So this looks like trans. 1, 2. Dichloro. Cyclohexane. Now, if I ring flip this by drawing the central 2 lines tilted the other way, drawing the right-hand line down and this one up, and oops, link it up if you can, a bit tricky. What was axial up becomes equatorial. What was equatorial, this chlorine, becomes an axial down. The equatorial here becomes axial up, and then we've got an equatorial H. Well, I think it's pretty clear that this is trans. Now the chlorine axial down, chlorine axial up. No doubt about it. Okay. Now we've got two structures, A and B. B really clearly shows off that it's trans. A is a little harder to see, but I think you can work it out that it is trans. Who is the more stable? Well, you were told that having axial occupancy leads to higher energy and less favorable structure, or less favorable conformation. So clearly structure A is the most favored conformation. And so if I was asked to draw a trans 1,2-dichlorocyclohexane, I would have to attempt to get structure A. Now, I would just randomly draw a structure, perhaps on scrap paper. To make sure it's trans, I would know, for example, that B, putting them axial, was trans. And when I did it on scrap paper, I'd remember axials are less favorable, so then I would just ring flip it on scrap paper, and then I'd draw the structure A that I've got. Now you may raise the question, do I have to draw 1,2 structures with the chlorines where you have? Could I maybe have used this carbon and that carbon? Well, yes, that's 1,2 as well. In fact, it's exactly the same thing because all you're doing is rotating about that axis. You're just spinning the molecule. Well, I guess you're spinning the other way. Okay, so you're spinning that way, rotating this molecule. So this carbon would become that one, and this carbon would become that one. You'd just be rotating it. And if you make a model of this, you can actually see that. So yes, to answer your question, your unspoken question, you don't have to put the chlorines where I have put them. As long as they're beside each other, as long as they're on adjacent carbons, they're 1,2. Okay, let's try modifying this now and taking a look at 1,2 in the cis case. Okay, so I'm going to put a chlorine up axial. Notice if you switch only one end, and what I've done is drawn exactly A, but I'm going to call this one C. C is A, but the first carbon, I switched the H in the chlorine. Now if I switch at one end of the molecule, and it originally was trans, I must have turned it into cis. Now you can actually see this because it's pretty obvious that the chlorine on the first carbon is straight up. The other chlorine's tilted up, which means they're both on the same side. It's hard to see, but they are on the same side, so they're cis. So this is cis. 1 and 2 dichloro. Cyclohexane. Okay, let's ring flip it. To do that, I draw two parallels tilted the other way. Draw it like that. Join up my lines, trying to make them parallel. Parallel is not a problem. Straight is a problem when you're using a pen mouse. Now, the chlorine that was axial becomes equatorial. The H is now axial. The chlorine that was axial, or the chlorine that was equatorial, now is axial, and its H is equatorial. Again, we have both chlorines up on the same side, cis. Is there a major minor conformer? We found that A was the most stable conformer and B was the least stable conformer. In the case of cis 1,2, structure C and D, is there a more stable or least stable conformer? Well, if we look at C, C has the chlorine axial and one chlorine equatorial. Ring flipping gives you one chlorine axial, one chlorine equatorial. It's an axial-equatorial combination that switches out. There's no gain. There's no change. So C and D must be the same energy. So what's interesting here is structure A. Well, in the trans 1,2-dichlorocyclohexane, you have one conformer that's more stable than another. In the cis 1,2-dichlorocyclohexane, if I say draw the most stable conformer, you can draw either one because they're of the same stability. Fascinating. Okay, let's try this now with 1,3-dichlorocyclohexane. Okay, let's see what we get with 1,3. Try to draw two parallel lines here. Here we go. All right, so I'm going to do 1,3, and I'm going to put a couple chlorines on. So let's start with an H, Cl, and this time we'll put Cl here at 1,3 and an H. Okay, what have I drawn here this time? Well, if I localize, put dots for the carbons, I've got a chlorine pointed down from a carbon. I have a chlorine that's pointed up an axial, down. It looks like it's opposite. This looks to me like we've got trans 1,3 dichloro cyclohexane. And let's do a ring flip. So I draw my central parallel lines tilted the other way. Draw one up, draw one down. You should practice doing this. The H that was axial now becomes equatorial. The Cl that was equatorial becomes axial. The chlorine that was axial is now equatorial. The H that was equatorial becomes axial. One chlorine's down, one chlorine's up. This is trans 1,3-dichlorocyclohexane. Is one of these conformers more stable than the other? Well, this time for the trans, we're getting the axial equatorial combination. Axial, equatorial. So ring flipping turns your axial into equatorial, but your equatorial into axial, so there's no net gain. You have one axial, one equatorial in both structures. Neither structure is more stable than the other. What's interesting is the change that when we went from 1,2-dichlorocyclohexane to 1,3, where in 1,2 this phenomenon was observed for the cis isomer. In the 1,3 case, it's observed for the trans isomer. That must mean there must be a difference in the cis. So let's take a look at the cis isomer if we can. Okay. So what I'm going to do is switch the H and Cl on the first carbon and keep the Cl and H the same on the other carbon. And if I change only one carbon substituents, I should have the new geometric isomer. And it stands out pretty clearly here. Both chlorines are up, both are above the ring, on the same side of the ring. This must be cis 1,3 dichloro cyclohexane. Okay, so now what we have is we want to draw the ring flip structure and see if we get a more or less stable conformation. So the center two parallel lines I tilt the other way. Okay, and so the Cl that was up becomes equatorial. The H is down. Cl is now equatorial. It's harder to see that these are both pointing up. They angled up a little bit, but these are two chlorines on the same side. But now they've both gone equatorial. And so this is cis-1,3-dichlorocyclohexane. But because we have both chlorines equatorial, we've produced a more stable conformer. This is a more stable conformation than the diaxial case. And so if I said draw the more stable conformer, you would have to draw the one on the right. Well, let's check one more case before we finish up. And let's look at the trans and cis 1,4-dichlorocyclohexanes. Now in the case of trans 1,4-dichlorocyclohexane, we can draw two ring-flipped chair conformers. The one is very easy to see that it's trans. There is no doubt that one chlorine is up and the other chlorine is down. But if we ring flip this, this chlorine here that was axial becomes equatorial. And this chlorine right here that was axial becomes equatorial. Where's my H? Because they're less pronounced, one up, one down, it's a little harder to see. But this represents, okay, A is the less stable, B is the more stable conformer. But they are both trans 1,4-dichloro cyclohexane. Now, what about the cis? If we take a look at the cis, if we go cis 1,4, well, if one chlorine is up, to be cis, or above the plane, the other chlorine must be above the plane. And what's interesting is when it's cis, one chlorine, oops, that's a chlorine, is axial, and one chlorine's equatorial. So if you do the ring flip, produce the other conformer, you get this chlorine now becomes equatorial. This chlorine now becomes axial. We still have one 4-dichlorocyclohexane, but this time cis. One 4-dichlorocyclohexane. The main point of all this is that since one is equatorial and one is axial, when you ring flip, you get an axial equatorial. The positions switch, but all you have is axial equatorial. Both A and B are the same. There is no structure that is more stable or less stable. So if you're asked to draw the more stable conformer, in the cis case, you can draw either one of these. Whereas in the trans case, you had to either draw A, the less stable structure, or B, the more stable structure. Well, there you have it. We've covered a lot of ground in this podcast.